All right, so you've watched part one of the screencast for electric current and resistance. That's the theory. Now, part two will be some examples. So you should know these relations from part one, which we'll need to use. First of all, electric current. We define several quantities. There's the current in a wire. Now, that'll be denoted I. There's the current density. That'll be denoted J. And that's a vector. The current in a wire is not really a vector. It just goes in the direction of the wire. But J gives me the current density at a point in a metal, let's say. So I'll have to know what's the direction of the current flow at that point. So J will be a vector. And it was shown in the part one that the current density is given in terms of the drift velocity. It's the charge of the current carrying particle, which for a metal would be an electron, so that's a charge minus E, times the density of the current carrying particles, so that will be the density of the electrons, the number per unit volume, times the drift velocity. That's the mean velocity as the electrons move along in their current. Now we can check the units. E is coulombs. Number is meters to the minus 3, number density. And velocity is meters per second. So we have here, well, coulombs per second is amps. So that's amps meters to the minus 2. So amps per meter squared. So it's current density. It's the current per unit area. And the current is defined as the direction of motion of charge. But electrons are negatively charged. So the current will be opposite to the current vector will be opposite to the displacement, the drift velocity vector. All right, so that's one topic from the theory. And the other topic has to do with resistance and Ohm's law. Ohm proved in experiments that the current in a wire with a potential difference, delta V, those two quantities are proportional, and the constant of proportionality is called the resistance, R. So I is delta V over R. For a given potential difference, a larger resistance corresponds to a smaller current. Now, it's also shown that R for a wire is a constant, rho, that depends on the material. That's called the resistivity. And times the length of the wire divided by the cross-sectional area of the wire. So if you have a long wire, with a cross-sectional area A and a length L, the longer the wire, the more resistance. But the larger the cross-sectional area, the less resistance. And the constant of proportionality, rho, just depends on what this wire is made of. You know, it has a value for copper, it has a different value for silver, it has a different value for, let's say, aluminum, and so on. That relates current in a wire to the potential difference across the wire. There's a more fundamental relation which relates the current density, that's J, at a point X in a material, to the electric field at that point. The current density is proportional to the field, just like the current in a wire is proportional to the potential difference. Well, in the same way, the current density is proportional to the electric field. And the constant of proportionality there is called sigma. Sigma is called the conductivity. And sigma is 1 over rho. So there's a material property. You could either give resistivity or conductivity. They're just inverses. Here's an example calculation. Calculate the drift velocity of the conduction electrons in a wire. So we have electric current in a wire. Let's call that I. So the electric current is I. And we have the conduction electrons are responsible for that current. All these little negative charges are moving in the opposite direction in a kind of a coherent way. Of course, each electron has some random motion, which depends on the temperature of the wire. But if we take the average of all those velocities, we'll get a uniform kind of coherent motion in that direction, and the average velocity will be what we call the drift velocity. And the problem is to calculate the drift velocity. In other words, calculate the value. Well, we have to know what's the current, and we also have to know what's the area here. So here's the area. So in order to solve the problem, we'll have to know the value of the current and the area, the cross-sectional area. So I'll assume that I and A are given. Now I have these two equations. The current density is minus E n V sub d. This n is the density of conduction electrons, number per unit volume. And I also have the relation that current density is current divided by area. Remember, it's amps per meter squared. Current is amps, area is meters squared. All right, well now the unknown is, what I'm trying to calculate is V. E is known. Well, I assume that A and I and A are known. What's N? N is the density, the number density. It's the number in a cubic meter, let's say, of the material. Now, this isn't the density of electrons. This is the density of conduction electrons. Not all of the electrons can move away from their atomic positions. You know, there's a nucleus for each atom which holds the electrons in place. For most metals, there's one conduction electron per atom. In other words, one of the, well, let's say it's copper, one of the electrons in a copper atom is free to move long distances throughout the wire and make up a current. So that means that the number density of conduction electrons is equal to the number density of atoms. Now, what's the number density of atoms? Well, you could get that from the mass density and the atomic mass. So if this is copper, copper has a certain density of mass. That's mass density, kilograms per cubic meter. Well, let's call mass density mu in this calculation. And copper has a certain atomic mass. There's a certain value for the mass of one copper atom. So if you take the kilograms per cubic meter and you divide by the kilograms per atom, you get the atoms per cubic meter. Now, I haven't given numbers here, but let's make a rough estimate. Let's say mu, that's a material property of the copper, is something of the order 10 to the fourth kilograms per cubic meter. That would be more or less the order of magnitude anyway. And let's say m, the atomic mass for this material, whatever it is 100 daltons. This is not correct. A dalton is 1.66 times 10 to the minus 27 kilograms. Well, let's say m is 100 times that. All right, so now the drift velocity will be J, that's I over A, divided by E, that's 1.6 times 10 to the minus 19, divided by the number density. Here we have the number density, mu over m. Well, I said mu was 10 to the fourth. I said m was actually 1.66 times 10 to the minus 25. So that would be 1 over 1.66 times 10 to the 28th, I guess. So that's the number density. It's the number density of atoms. It's also the number density of conduction electrons, because for each atom there's one conduction electron. Well, again, I'm just making a kind of a rough estimate. I and A will be of order 1 in standard units. You might have 1 amp and, I don't know, 1 centimeter squared. So I and A will be numbers not far away from 1. E, of course, is much less than 1. I'll divide by that. The number density is much greater than 1 if I use standard units. So E would be 1.6 times 10 to the minus 19 coulombs. N would be something of the order 0.6 times 10 to the 28th per cubic meter. Now, these are very large numbers. Well, this one's very small. This one's very large. When I multiply them together, I get something like 10 to the power 9. And that's in the denominator. So that will be 10 to the minus 9 in the numerator. So you see the drift velocity is going to be a number, depends on the current in the area, but it'll be a number of order 1 in standard units times, well, let's say divided by 10 to the power 9 or multiplied by 10 to the power minus 9. It'll be very, very slow. So drift velocities are very slow. Electrons moving in a current in a wire, for currents of the order of an amp, for wires of the order of a centimeter, are very slow. There'll be an example of that in the log kappa assignment. Here's another example. This is taken from the textbook by Bauer and Westphal. It's exercise 25.47. It's got 2 parts, A and B. So A has a light bulb connected to a battery, and there's information given about the current and the voltage of the battery. And the question is, what's the resistance of the filament? The resistance is predominantly in this filament. The wire that connects the battery to the filament, has resistance very small. So that's part A. Part B has two identical light bulbs, same battery, and now what's the resistance of each bulb? Now you might think, well, the resistance of a light bulb is a constant, so the resistances here would be the same as the resistance in part A. But we're going to find out that's not the case. Because the measurements, 4.1 amp, 6.2 volts, and then 2.9 amps, 6.29 volts, those imply different resistances in case B than in case A. We'll have to think about why that could be true, because all the light bulbs are the same. So part A is very simple. Part A is to calculate the resistance of the filament, and we use Ohm's law. It's the potential difference across the filament, and neglecting any resistance in the wire, that's just the potential difference across the electrodes of the battery. So that's 6.2 volts divided by the current. The current has been measured to be 4.1 amps. So resistance can be written by Ohm's law as potential difference across the resistor divided by I. You know, delta V is IR, or I is delta V divided by R. So a larger resistance produces a smaller current. Well, if you rewrite the relationship this way, R is delta V over I. And so you calculate these numbers, you get 1.512 ohms. So that's the answer for A. Now, what about B? Well, here we have two resistors in series. We have a resistance and then another resistance. And you know from resistors in series, that's equivalent to one resistor, where this equivalent resistance is R1 plus R2. So in your previous course on electricity and magnetism, you probably learned how to combine resistors in series. You just add the resistances. Resistors in parallel is different. There you add the reciprocals of the resistances. Well, here we have two resistors. They're identical. So the combined resistance is 2 times the resistance of one bulb. So this is our bulb for part B. This is our bulb for part B. Total resistance here is 2 times that. And again, that'll just be the potential difference, which is measured by a voltmeter to be 6.29 volts, divided by the current, which is measured by an ammeter to be 2.90 amps. And if we calculate the number, it's 2.169 ohms. Now we want to know what's the resistance of one of these light bulbs. So we have to divide by 2. We got 1.084 ohms. Well, RA and RB are different. So how can that be? It's assumed that these numbers are taken from measurements. So you find a different resistance in this case than this case. How could that be? Well, remember, there's another resistance in the problem. There's the resistance of the battery, which is called internal resistance. And this is explained in the textbook. So for both of these problems, you have to also remember there's an internal resistance in addition to the light bulb resistances. And since I have two identical batteries, they'll have the same internal resistance. So I have to have these two equations taking into account the resistance in the battery. The EMF of the battery has to be the current times the internal resistance plus RA. And the EMF of the battery, in the second case, has to be the current over the total resistance. And again, these are three resistances in series. You know, the current has to go through the battery and then through the two filaments, so those resistances are in series. So the total resistance there would be R internal plus 2 times RB. Now this delta V is not the internal, is not the EMF of the battery. This 6.2 volts is the voltage across the light bulb, measured by a voltmeter, and similarly this 6.29 volts. So what's not given in the problem is the EMF of the battery. But these equations determine the EMF of the battery. So you see, you have RA from part A, you have RB from part B. You have here two equations with two unknowns. The two unknowns are the EMF of the battery and the internal resistance of the battery. And the values measured for RA and RB imply, to solve these two equations for two unknowns, the EMF of the battery is actually 6.508 volts. That's the same in part A and part B, and not equal to the voltage across the light bulb. And also the internal resistance is 0.075 ohms. So it has a small internal resistance. You know, the internal resistance is quite a bit smaller than either RA or RB. But that is the size of the internal resistance, which would account for this difference in the resistance from the measurements. There's another issue here. Resistance depends to some extent on the temperature. Now, the temperature of the filament in a light bulb is extremely high. These are by no means at room temperature. It's so high, it's white hot. You know, when you start the current, the filament will turn red hot, and then it'll get even hotter. It'll turn white hot. It'll turn so hot that it emits white light of all the wavelengths. And so these filaments have very high temperatures, and they'll have different temperatures. And so this filament, or the filaments in this case, will end up with a lower resistance because it's not as hot as the filament in this case A. So to account for the fact that the two measurements give different values for the resistance, first of all, you have to take into account the internal resistance of the battery to figure out what the what the EMF of the battery is. And they can turn out to be different because they'll have different temperatures. And again, this is something that's explained in the textbook by Bauer and Westphal, the temperature dependence of a resistor. Here's a third example. Again, it's a problem at the back of the chapter 25 in the textbook by Bauer and Westphal. It's exercise 2570. It says, what are the resistance and the radius of a 3.5 meter long iron heating element for a 110 volt, 1500 watt heater? So in other words, you have a heater which has a long heating element and this will have some resistance across this heating element. If you pass current, let's say a current I, into the heating element, there's resistance here. Let's say the length of the heating element is L, that's 3.5 meters. Well, because of the resistance, it'll get hot. It'll get red hot. You know, you'll have a red hot wire here, 3.5 meters long, and that will radiate infrared waves and also some visible light waves. That's why it looks red. So there'll be infrared and maybe some red light waves. That's the heating. And the power, it says, is 1.5 kilowatts. So the information you're given here is the power is 1.5 kilowatts. So you're given various information. You're given the length, you're given the power. You're not given the radius of the wire. Let's call the radius of the wire little r. In fact, that's question B. So in a problem like this, we need to write down what we know, and we need to write down what are the equations. So here are the things that are given. Delta V is 110 volts. 110 volts. Power is, well, 1,500 watts. So that's the power. We're also given the length of the wire, 3.5 meters. There's one more piece of information we're given. It's made of iron. The answer is going to depend on the resistivity of the material. Will it be the resistivity of iron? Now we can look that up. So another piece of information is the fact that the filament is made of iron, and from that we can determine the resistivity. There's a table in chapter 25 of the textbook which gives the resistivities for a number of different metals. All right, so that's the given information. Now what we're trying to calculate is the resistance. We'll call that R, and the radius. We'll also call that R, but not capital R. We'll call that little r. Now what equations do we know that will relate these various quantities? Well, we know from part 1 of the screencast, the resistance of a wire is rho L over A. And of course, the cross-sectional area of the wire is pi r squared. So there are some equations that relate the various quantities. We also know the power in a resistor. The power dissipated in a resistor. As current flows through a resistor, You have current I going in one side, current I coming out the other side. Energy is converted by heating, so that's called joule heating. Um, the energy dissipated in a resistance, carrying current I, is I squared R. Or you could rewrite that as delta V squared divided by R, because I times R is delta V. So I squared times R is delta V squared divided by R. So these are the equations that we have. And again, you should be sure you have these written down in your notebook. I hope you're taking notes, because these equations will be necessary for some of the law and kappa problems. This one, I think, is explained in the screencast part 1. This one I don't think is explained in the screencast. You'll find that by reading the textbook. All right, so now you have to put all these equations together to calculate R and rho. But you see, you sort of have two unknowns, R and rho, and you sort of have two equations. So two equations of two unknowns, you should be able to find the answer. Here's a little computer program to do the calculation. The first thing we can calculate is the resistance using this equation. The resistance is delta V squared over the power. So the resistance is delta V squared, that's 110 squared, divided by the power, that's 1500. And that gives you the answer, 8.07 ohms. So that's part A. Now part B, well, once we know R, we can use this equation to solve for the area. The area will be, move this to this side of the equation, move this to the other side of the equation. Area will be rho L over R. We just calculated R. So we'll have rho for iron, that's 9.7 times 10 to the minus 8. You have to get that from the table of resistivities. L, that's 3.5 meters, divided by R. Well, R I just calculated. It's that 8 ohms. So that will give you the area. Now you could do this with a calculator, but it's a little easier if you do it with a computer program. So, you could do this using Wolfram Mathematica, or you could use Python or something like that. Or you could just use a calculator. Well, this gives you the area. Now we have to calculate the radius. Well, the radius is the square root of a divided by pi. So we take the square root of a divided by pi, we get the radius. So this is the kind of problem where you have to put together a number of different pieces of information and a number of different equations. And there'll probably be some similar problems on the law and kappa assignment. Well, here's one more example. This is, again, an example taken from the textbook by Bauer and Westphal in chapter 25, exercise 80. In fact, this is one of the homework problems. This is called CC 245. So that's one of the homework problems. You have a piece of wire in the form of a circle. And now you want to know what's the electrical resistance between points A and B at room temperature. So in other words, you're going to connect a battery at point A and at point B. So here's some kind of battery or something which will drive a current. which will drive a current. It has some, so there's some potential difference, and there's some current going in here. Oops, I have this wrong. Current will be taken out. Current will be going in here. So the current will be going in here, the way I've got the battery here. The positive electrode will deliver current to point B, and there'll be a current coming out from part A and going back into the negative electrode of the battery. So I have a loop of current. And I guess it tells you that it's copper. All right, so we have to calculate the resistance between 2 points. Let's say the wire has length L and cross-sectional area A. So the circumference of this circle is L. Circumference of the circle, but it's the length of the just the length of the wire, the copper ring. And it has cross-sectional area. So the area of the cross-section of the wire is A. So here's a little cross-section of the area of the wire. It's a little area A. And we'll assume that those are given. Now, the trick of this problem is you actually have two resistances in parallel. You see, this current I will divide into two parts, I1 along this direction and I2 along this direction. So here's I1 going from A to B, or from B to A rather, along the short arc, and then I2 going from B to A along the longer arc. And then they come together again at the point A and go out along this wire into the negative electrode of the battery. So you see I have two resistances in parallel. The full current divides into two parts, passing those two resistances. So this first resistance is rho L over A, where L is the length of the wire from B to A. Well, that's 1/4 of the circumference, because this angle is 90 degrees. There's a right triangle. There's a right angle. So R1 will be rho times 1/4 L divided by A. And R2 will be the resistance for this long wire. It'll be rho 3/4 L divided by A. And now for resistances in parallel, remember the equivalent resistance is R1, R2 over R1 plus R2. This is how you combine resistances in parallel. You don't add the resistances, you add 1 over the resistance. That gives you 1 over the equivalent resistance. Or the equivalent resistance, the total resistance, is R1, R2 over R1 plus R2. And that's the quantity you're supposed to calculate in the problem.